Good morning. Last time we talked about sampling. This time we're going to talk about reconstruction. In other words, if we have a discrete signal, how do we recover the original continuous time signal again? Now it turns out that doing this in frequency is much easier to see what we have to do. So let's see what we have to do. Now, before we start, the first thing I'm going to mention is to be able to recover the original signal, there can't be any overlap between any of the original signal and its copies, as we saw, things that we called aliasing. And so in other words, we're going to assume that the analog signal, when it was sampled, was band limited to omega m, and that the sampling frequency is going to be greater than 2 times the greatest frequency in that signal. Now, when we sampled, we got this thing here, right? There was an original spectra, and when we sample, we get this. Now, let me go over this once again, just to go through it, right? The spectra of the discrete signal is going to be the sum of these spectra. Now, let's say k is equal to 0. So we'd have x of a of j omega over t. What would that look like? Well, that would be this term here. When k is equal to 1, we'd get this term here. When k is equal to 2, we'd get another spectra at 4 pi. When k is equal to minus 1, we'd get this one here. So it's always shifted by 2 pi. Now this is what we have. What we want is this spectra here. We want to be able to recover the original spectrum again. So how do we go from here to here? Now if we look at it, we can see what we have to do, right? Here I wrote it out. We're going to do this in 2 steps. We need to change from little omega back to big omega. We need to go from radians per sample to radians per second. And we need to filter. If we look at it here again, right, we need to go from samples to second, and we don't want all these spectra, so we need to eliminate all of the spectra except this one. How do we do that? Well, we filter everything. We just leave these frequencies here. Since these are the frequencies that are close to 0, this would be the low frequencies. So we'd have a low-pass filter that eliminates all of these copies and only gives us the original spectra again. So writing this out, it would look something like this. So this would be the spectra in radians per sample. It's small, but it's supposed to be the same image we had up there. This would be the spectra. Now the first thing we do again is we change from radians per sample to radians per second. This is what we're going to call our analog converter. And we have the relation between little omega and big omega here. 0 is going to be 0, right? Now 2 pi is going to be omega s, which would be 2 pi times f of s. And once we have this spectra, as I mentioned above, we want to get rid of everything except this spectrum. So we put it through a low-pass filter to get this. Now let's go through it. So we start off with this signal here. First we're going to change from little omega to big omega. We know the relationship between the 2 omegas. We can write it like this. For example, big omega is little omega times f of s. So this would be just omega m. 2 pi would be 2 pi f of s, etc. So we can get all the frequencies for radians per second. And then once we have this spectra, we put it through a low-pass filter to eliminate all the copies. Now, what frequency are we going to cut off in our low-pass filter? Well, we know that this frequency is 0. We know that this frequency is 2 pi s. The highest frequency we can have without there being overlap would be halfway between them, right? If omega m gets bigger, this will get bigger, but this term over here would get smaller. And so they come together and then meet right at pi f of s. So as long as omega m is less than pi f of s, well then we're okay. And if that's the case, we can recover the original signal. And so we make our low pass frequency the highest frequency possible that we can use. So if we write this out, we can say that our spectra, our analog spectrum, is going to be this spectra once we change little omega to big omega times t, and then we pass it through the filter. Now remember, our filters are linear time invariant systems. So passing it through the filter, if this is the input and we want the output, it'll be a convolution in time, but it'll be a multiplication in frequency. And so this would be our output. We take our input, multiply it by the filter to get our output. Now looking at this in time, we can change this to time. Now this of course is a multiplication in frequency, so it'll be a convolution in time. And so it would be the inverse transform of each of these terms. So we have to find the inverse Fourier transform of each of these terms to be able to solve for xa of t, or the equation. Let's look at the filter first, because that's probably the easiest part. Let's take the inverse Fourier transform of this thing here. Now we know what an inverse Fourier transform looks like. It will be like this. Now this thing here, h of a, we made it to be either 1 or 0, right? It's 1 between minus pi f of s and pi f of s, and it's 0 after that. And so our integral is not going to go from minus infinity to infinity. It's going to go from minus pi f of s to pi f of s, and in that interval, it's going to be equal to 1. And so we have this. And so we just evaluate this integral, and it turns out that this is a sinc function, right? It's going to be, if we get it to a sine, it'll be sine pi t over t times 1 over pi t. Now we have a t here and we have a t here. So if we define the sinc function as we did before, let's define sinc of x as sine x over x. Now there are different definitions of sinc functions. The one we're going to use is the one that's mostly used in math. Sinc is going to be sine of x over x. And so we need a 1 over t here to be able to write this as a sinc function. And this would be the inverse Fourier transform of our filter. Now, we know that a dtft is written like this. So this, if we change little omega to big omega times t, it would look like this. And we want to take the inverse Fourier transform of this term here. So we just substitute what the function is. Now, the Fourier transform and the inverse Fourier transforms are linear transformations. It's a linear transform, right? It's an integral. So we can interchange the order of the summation and the integral. So let's take out everything that doesn't have omega in it. And so we'll get the inverse Fourier transform of an exponential function. Now instead of going through all the problems, let me just say what it is. We know that an impulse is going to be 1 in frequency. And we know a shifted impulse is going to have this inverse, or this transform. Right? If we take the Fourier transform of delta t minus t0, it'll be this evaluated at t0. And so we see that this is going to have an inverse that's just an impulse. So this thing up here, we can see immediately it's going to be an impulse where it's going to be t minus nt, whatever is multiplied by the omega. So then coming back up here, we can write this function substituting what this is. And so what is the inverse going to be? Well, the inverse is going to be this summation substituting what the exponential is in there. So the inverse is an infinite sum of impulse functions multiplied by x of n. The best way to think about this is that this is going to be a bunch of impulses. The impulses are at every multiple of t. There's going to be one at 0, t, 2t, 3t, and not the amplitude because it's an impulse function, but the area of the impulse is going to be the sample we took at that time. Now, going back up to our original function, right, what we want to calculate is a function for x of t. We know that the filter is a sinc. We just calculated the inverse Fourier transform of the x of e to the j sigma nt, and we need to do this convolution. Okay. So that we see that the t immediately is going to cancel out, so we get a sinc and we get this. Now, when we do a convolution, as we know, one of the functions, we're going to write it as tau, and the other is t minus tau. So let's write the sinc as t minus tau, and let's write this function simply as tau. And so we'd get this function here. Again, let's interchange the order of the summation and the integral. We take out everything that doesn't have tau, and inside the integral we get this. We like this integral because, again, when we have these infinite integrals with impulses, it's easy to evaluate, right? It's just the function evaluated where the impulse is infinite. And we know that this impulse is infinite when tau is equal to nt. So we evaluate this function when tau is equal to nt, and this is what we get. Now, this is our final answer. This is our final equation, right? The signal, the reconstructed signal, what is it? It's a bunch of sinc functions shifted in time with different amplitudes. Now, let's take each of these terms. Let's look at them individually. For example, right, n goes from minus infinity to infinity. Let's take them one at a time. For example, if n is equal to 0, what would we have? We'd have x of 0, sinc of pi t over capital T. It would be a sinc function which has a highest point at 0, and the highest point would be x of n, in this case n equal to 0. So this, the black line, would be the term when n is equal to 0. That would be x of 0 times our sinc function. Now if we change n, let's say we go to n equal to 1, then we'd get x of 1, and it would be the sinc function again. The only difference is, instead of having the highest point at 0, the highest point is going to be shifted. N is equal to 1, so the highest point is going to be equal to t. So this is going to be equal at t. So the highest point is going to be equal to t, and it's our sinc, another sinc function. We can keep doing this, right? N equal to 2, n equal to 3. If n is equal to 2, well, it would be shifted to 2t, so the highest point would be 2t, and it would be another sinc function. The only difference is all of these sinc functions have different amplitudes because the x of n are different. Now, what are the x of n? Remember, the x of n are the samples we took at the different times, right? X of 0 is the sample we took at t equal to 0. X of 1 is the sample we took at t equal to capital T. X of 2 is the sample we took at 2t. And so we see that these sinc functions are kind of interesting. All of the sinc functions, we know that all of the sinc functions are 0 at 0 except one. The only one that's not equal to 0 is the sinc at 0. Again, and although I've only drawn 3 sincs, if we had lots and lots of sincs, the same thing would happen. At capital T, all of the sincs are 0 except one of them. And that one would be x of 1. Now, our reconstructed signal is the sum of all of these sinc functions. So I have an infinite number of sinc functions. I add them all together and I get my original signal again. Okay? Now, let's look at this in MATLAB. Let's say I take this signal. Down here in seconds, we're going to take a continuous time signal. We're going to sample it every half second. And here I took a sample at minus 0.5, at 0, 0.5, 1, 2, 1, 1.5, 2, 2.5, etc. So we have 1, 2, 3, 4, 5, 6. We have 7 samples of this continuous time signal. What would it look like? Well, my samples are just going to be, right, we're going to have a sample at minus 1, 0, 1, 2, 3, 4, and 5. Now, I want to reconstruct my original signal. I want to use this equation to go back to my original signal. Now, to be able to do this exactly, we need an infinite number of samples. Here we only took 7 samples, so we're not going to be able to reconstruct it exactly. But let's see how it looks. It would look something like this. Okay, so notice this will be sort of like what I tried to draw up above. We have a bunch of sinc functions, right? Here we have a sinc function that has a peak at 0. And notice that all the sinc functions are 0 except that one. Here at 0.5, all the sinc functions are 0 except the sinc function that has a peak. And so at these points, we know what the original signal was, and so we need the reconstructed signal to go through those points. What we're trying to determine is, between those 2 samples, what the original signal was. And so we use the sum of all these sinc functions to try to be able to reconstruct the signal. Now we can think about reconstructing the signal in lots of ways, right? If we looked at this signal and we say, what reconstruction would it be? Well, we can think of different reconstructions, right? We could just use a sample and hold. We could keep the sample until the next one and then go down and down and down. Or we could do a straight line between the samples. Now, for those of you who have read a little bit about interpolation, we can think of the first one as a constant sample. That would be the 0 order interpolation. Putting a straight line between samples would be a first order interpolation. If we do a second order interpolation, it means we'd use x squared, and so we'd have a little curve in here. If we keep doing this, interpolations of higher and higher order, when we get to infinite order, this is the equation that we have. So again, in this case, we only took 7 samples, so our interpolation is not excellent, but we can see that we did a pretty good job of reconstructing the signal, even though we only had 7 samples.